Hello, and thank you very much for tuning in to this talk on the dynamic complexity of reachability. How many changes can we handle? This talk presents joint work with Samir Datta, Pankaj Kumar, Anish Mukherjee, Anuj Tawari, and Thomas Zeume, and my name is Nils Vortmeier. As a start, let us consider social networks that we represent here as a graph. So the uses of the social network are represented as nodes, and there is an edge between two nodes if the corresponding two people know each other. Now we are interested in the query whether the two users Alice and Bob know each other through some intermediate set of people, so in terms of the graph, whether the Alice and Bob nodes are connected. And let's say that at this moment they are not connected. But social networks tend to be rather dynamic, so people get to know each other and edges are inserted into the graph. And let's say that after such an edge insertion, the Alice and Bob nodes are connected. On the other hand, people don't want to know each other anymore, so edges get deleted from the graph. And after such an edge deletion, the Alice and Bob nodes might be disconnected again. During all this time, we are interested in the changing query result, whether the Alice and Bob nodes are connected. But as the changes that occur to the graph are rather small, there should be something more sophisticated than just recomputing this query result from scratch after every change to our social network. And this is something that we try in the setting of dynamic query evaluation. Having a fixed query, we store some auxiliary data in addition to our input data, such that we can give the answer to the query. So usually the query result is just part of the auxiliary data. Whenever our input data changes, we update the auxiliary data based on its old version and on the change, such that we can again give the answer to the query. And that just goes on when further changes occur. Let's look at an example and see how the reachability query can be maintained under insertions of edges. So our goal is to maintain the answer to the reachability query, that is, the transitive closure relation T of an input graph G. So assume for the current version of our input graph that this relation is given. Now, how does the transitive closure relation change if an edge is inserted into our graph? We have to determine whether after the insertion of an edge UV, a path from X to Y exists, and such a path exists if it existed before the edge insertion, or if there were paths from X to U and from V to Y, and together with the newly inserted edge, those paths form then a path from X to Y. So we know how the updated transitive closure relation looks like. Now, instead of devising an algorithm and specifying how the updated transitive closure relation is to be constructed, we use a descriptive approach and use first-order formulas to express the update. The observations that we just had can directly be turned into an update rule for our transitive closure relation T after edge insertions. Whenever an edge is inserted, the result of the first-order formula that is part of the update rule replaces the transitive closure relation T. The class of all queries that can be maintained in this way, so using first-order rules to update auxiliary relations, is called an FO, and we have seen in the example that the reachability query is in the FO under insertions of single edges. Why do we use first-order logic as an update language? The first motivation comes from database theory. First-order logic corresponds to the relational core of SQL, so all queries in the FO can be maintained in a standard database system. On the other hand, there's also a motivation from complexity theory. First-order logic corresponds to the circuit complexity class uniform AC0, at least if it has access to a linear order and the arithmetic predicates plus and times. So all queries in DINFO can be maintained in a highly parallel fashion. Let's have a look at a more challenging example. We would like to show that the reachability query on undirected graphs is in DINFO under insertions and deletions of single edges. At first, we need to describe the auxiliary relations that we want to maintain in addition to our input graph. The first auxiliary relation is a spanning forest, and the second relation gives us in-between information for this forest. So a tuple ABC is in this in-between relation B. If B is between A and C in F, that means that On the unique path from A to C in the spanning forest, we will find the node B. Now we need to describe how these relations are updated after edge insertions and deletions. Edge insertions are easy to handle. If an edge is inserted between two connected components of the graph, then this edge becomes part of the spanning forest. If an edge is inserted inside one connected component, then no update is necessary. Now let's consider edge deletions. If the deleted edge is part of the spanning forest, then we need to determine whether there are alternative edges that can replace this deleted edge. Here in this example, there are actually two edges that can replace it, and we need to choose one. But so far we cannot differentiate between those edges in first order logic, so maybe we should maintain another auxiliary relation, namely a linear order on the nodes. Such a relation is easy to maintain. We just insert a node at the end of the linear order when the first edge for this node is inserted into the graph. With the help of the linear order, we now can tell a difference between the two edges E1 and E2 and take the lexicographically smallest one into the spanning forest. If, on the other hand, an edge is deleted that is not part of the spanning forest, then no update is necessary. Along these ideas, we can now construct update rules that witness that reachability on undirected graphs is in DNFO under insertions and deletions of single edges. We know several results regarding how reachability can be maintained in DNFO. For example, reachability for acyclic graphs is in DNFO under insertions and deletions of single edges, as is reachability in undirected graphs, as we have just seen. And also there's a quite recent result that reachability in arbitrary directed graphs can be maintained in DNFO under insertions and deletions of single edges. So regarding our opening example of social networks, we know quite well how we can handle changes that are insertions and deletions of single edges. But isn't it plausible to assume that in a real-world social networks, several edges are inserted and deleted at the same time? That is why we study the question whether reachability can be maintained under changes that are more complex than just single edge changes. And of course, when we want to do that, we need to discuss which kind of changes we want to consider. Allowing arbitrary changes might not be a good idea here, because when we allow our input instance to change arbitrarily in one step, then there's no reason to assume that the information that we stored for the old instance is in any way helpful for the instance we have now. So changes need to be restricted in some way. One possibility to do that is to consider changes that adhere to some structural property. For example, you are allowed to insert multiple edges, but only one inside each connected component. Another possibility is to study changes that are specified as a result of a query on our input instance. For this talk, we consider another option, which is bulk changes of restricted size. For this kind of changes, we are given a function f, and if our input graph has n nodes, then in one step we are allowed to change f of n many edges. Some results for these kind of changes have been published at ICALP 2018. There we have shown that reachability is in DNFO with arithmetics under insertions and deletions of log n over log n many edges. DNFO with arithmetics here means that our update rules have access to a built-in linear order and to corresponding addition and multiplication relations. You can also think of updates that are specified by uniform AC0 circuits. If we additionally allow our update rules to use majority quantifiers, then reachability can even be maintained under insertions and deletions of a polylogarithmic number of edges. In DNFO plus majority with arithmetics, updates are equally expressive as uniform TC0 circuits. In this paper, we continue working on the question how many changes we can handle when maintaining the reachability query. The contributions of this paper are as follows. We show that reachability on undirected graphs is in DNFO with arithmetic under insertions and deletions of polylogarithmically many edges. From the proof of this result, one can easily see that reachability on directed graphs can be maintained under insertions of edges of that size, but we cannot allow for any edge deletions there. If we allow our first order update rules to additionally use modulo 2 quantifiers, then reachability can be maintained under insertions and deletions of polylogarithmically many edges for all classes G of graphs for which polynomially bounded non-zero circulation weights can be computed in NC. I will explain later on what that actually means. Such weights can be computed for planar graphs, and here we also show that they can be computed for graphs with bounded tree width. We also observe that reachability is not in the NFO plus mod 2 with arithmetics under changes that are larger than polylogarithmic in the size of the graph. So our results are optimal with respect to the size of the change that we allow. Our proofs make use of an observation that I would like to mention here. This observation is that our update rules can express all NL computable queries on subgraphs of polylogarithmic size by evaluating a first-order formula on the whole graph. This observation can be proved as follows. It is quite well known that reachability on graphs with n nodes can be decided by circuits that have depth 2d and size n to the order dth root of n for every d. Now, if capital N is polylogarithmic in the number of nodes of the graph, and we choose a suitable d, then the circuit size is actually polynomial in the graph size. But that means that there are uniform AC0 circuits for reachability on subgraphs of polylogarithmic size. As uniform AC0 is equivalent to first-order logic with arithmetics, there's also a first-order formula for that. The observation then follows from the fact that reachability is complete for NL under first-order reductions. With this observation in mind, we can now proceed to the proof of one of our main results, that reachability on undirected graphs is in DNFO with arithmetics under insertions and deletions of polylogarithmically many edges. Here, I would like to give you the proof idea for deletions. Handling edge insertions is quite easy if you know this step. The goal is to maintain the same information as we did in the example before, so a spanning tree of our input graph and its in-between relation. If some set of edges is deleted, then the spanning tree S gets disconnected and decomposes into different connecting components. On these connected components, we define a graph H. For each connected component, H has one node. There is an edge between two nodes of H if there is a non-spanning tree edge in the graph G remaining after deletion that connects both connected components that these nodes stand for. Observe that if a polylogarithmic number of edges gets deleted, then the graph H has only polylogarithmic size, so there's only a polylogarithmic number of nodes. As our update rules can express every NL computable query on graphs of that size, they can define from scratch a spanning tree of H and its in-between relation. And using this information, it is quite easy to also update the auxiliary relation of our input graph G. So, reachability and undirected graphs can be maintained under edge deletions of size polylogarithmic in n, and with similar ideas, it can also be shown to be maintainable under insertions of polylogarithmically many edges. Now we proceed to our second main theorem concerning reachability in directed graphs. This result states that reachability can be maintained in the NFO plus mod 2 with arithmetics under insertions and deletions of polylogarithmically many edges for all classes of graphs for which polynomially bounded non-zero circulation weights can be computed in NC. As I've mentioned earlier, examples for such classes of graphs are the classes of planar graphs and graphs of bounded tree width. This result enhances a result from our ICALP-18 paper that reachability on all directed graphs can be maintained in the NFO plus majority under insertions and deletions of polylogarithmically many edges, in the sense that it only applies to some classes of directed graphs, but it lowers the complexity of the updates for these graphs. Its proof is an adaptation of the ICALP-18 proof, and I will now sketch its ideas. The proof uses a linear algebra approach. So let A be the adjacency matrix of our input graph G. If we look at the ith power of A, then the ST entry of this matrix gives us the number of paths of length I from S to T in our input graph. If we introduce a formal variable x and do not look at the ith power of the matrix A, but at the ith power of the matrix A times x, then the ST entry of this matrix is a monomial C1 x to the I, and again COI gives us the number of paths of length I from S to T. Let C be now the infinite sum over the matrix powers AX to the I for all I. An ST entry of this matrix is a formal power series, and its coefficients give us the number of paths of the corresponding length. In the ICALP-18 paper, it was shown that the first n coefficients, C0 to Cn-1, can be maintained in D4 plus majority under the changes of polylogarithmically many edges. This is sufficient to tell whether a path exists between S and T, because if such a path exists, there's also a path of length at most n-1. And if a path of length at most n-1 exists, then one of the coefficients that we maintain is non-zero. So how can this proof be adapted towards FO plus mod 2 update rules? One can observe that all involved computations can already be expressed by FO plus mod 2 formulas if the computations are done modulo 2. That means that we can maintain in D4 plus mod 2 with arithmetics the first n coefficients C0 to Cn-1 modulo 2. But if for some I the value of Ci that we maintain is 0, does this mean that there are actually 0 paths of length I, or is there a non-zero even number of paths? To circumvent this problem, we need to ensure that if some path at all exists, then for some length I, there should be an odd number of paths of length I, and ideally there would be just one path of length I. To achieve this, we now consider weighted graphs. Especially interesting for us are weighting functions that isolate a graph. Such an isolating weighting function maps each edge of the graph to a natural number, such that for each pair S of t of nodes, the following holds. If there is a path from S to t at all, then there is a unique path that has minimal weight under the weighting function. Note that if we have isolating weights available for our input graph at all times, the adaptation idea that we formulated on the last slide works. There is a unique minimal weight path, so if we know for every number L whether there is an even or an odd number of paths with total weight L, we can correctly answer reachability. Of course, now the problem is to maintain isolating weights for our input graph under insertions and deletions of edges. To be able to do so, we will use non-zero circulation weights. A weighting function has non-zero circulation for a graph if it maps each edge of the graph to an integer, such that the total weight of every directed simple cycle in G is non-zero. If we have non-zero circulation weights given, then we can easily obtain isolating weights by adding a common number to all weights of the edges. The proof of our result that reachability can be maintained on all classes of graphs for which polynomially bounded non-zero circulation weights can be computed in NC now goes as follows. At first, we show that we can maintain reachability for one change of a polylogarithmic number of edges. Let's assume that we are given polynomially bounded non-zero circulation weights for our input graph G, and that there is a set delta E of edges that are inserted and deleted, and that set delta E is of polylogarithmic size. We show that FO plus mod 2 update rules can determine new weights for the changed edges such that the resulting weighting function isolates the changed graph, and again the weights are polynomially bounded. Using the ICALP-18 approach mentioned earlier, we can now give the answer to the reachability query after this particular change. Notice that we start with non-zero circulation weights, and it is actually important in our proof that we have these kinds of weights, but end up with isolating weights, from which we cannot readily obtain non-zero circulation weights again. So we cannot repeat this part for further changes just like that. But here we can apply a general technique that was introduced for an ICALP-17 paper, generalized for ICALP-18, and that we further enhance for this paper, that tells us that this is actually enough. This technique gives us that if we can maintain reachability for one change of a polylogarithmic number of edges using auxiliary relations that are computed in NC, then reachability can be maintained in D4 plus mod 2 with arithmetics under an arbitrary number of changes where each change might insert or delete a polylogarithmic number of edges. Together, this proves our result. Let's come to a conclusion. We have seen that reachability in undirected graphs can be maintained in D4.F with arithmetics under insertions and deletions of a polylogarithmic number of edges. Additionally, for directed graphs, reachability in planar graphs and bounded two-bit graphs is in D4.F plus mod 2 with arithmetics under insertions and deletions of polylogarithmically many edges. This holds also for all other classes of graphs for which polynomially bounded non-zero circulation weights can be computed in NC. All these results are optimal with respect to the size of the change. We cannot maintain reachability under changes of more edges within this complexity. If we only allow insertions of polylogarithmically many edges and no edge deletions at all, then reachability in all directed graphs can be maintained in D4.F with arithmetics. If we only want to consider D4.F and want to allow both insertions and deletions of edges, then the ICALP-18 result is still the best available result for reachability on directed graphs. It can be maintained in D4.F under changes of log n over log n size. It is still an open question for which classes of directed graphs one can maintain reachability in D4.F under simultaneous insertions and deletions of polylogarithmically many edges. With this, I would like to conclude my talk. Thank you very much for your attention. If you have any questions, comments, or you want to know more, please don't hesitate to contact me. Thank you again, and goodbye.